Hi there and welcome to Olago Academy. Alright, for today's video lesson, we are continuing on the topic which is elastic properties of a solid. We have explained elasticity. I've explained elasticity. I've done the example explaining Hooke's law. I've explained Hooke's law using a particular diagram on the board, and also I've done some calculations on elasticity. You can check out the video on my playlist. Alright, for this video lesson, be considering stress, be considering strain, and be considering Young's modulus and some few examples to solve. Alright, in the context, within the context of elasticity, what is stress? Stress is simply the ratio of the force applied on an elastic material to the area in which the force is being applied. Once again, stress is simply the ratio of the force applied on an elastic material to the area in which the force is being applied. Alright, mathematically, we are saying that stress, which is having a symbol of sigma, equal to, we said, is the ratio of force to area. So we are expressing force over area. So this is the expression for stress, the ratio of force to area. Alright, so we have this. Now force is measured in Newton, and area is expressed as meter squared. So we can express the SI unit of stress, which is sigma, to be having, or let me say the SI unit to be Newton per meter squared. So we have this as the SI unit for stress. It can be this way or it can be this way, like this. So this is the SI unit for stress. Alright, now let's consider strain. What is strain? Let's consider strain. And it's having a symbol referred to as epsilon. This is here. Epsilon is having a symbol referred to as epsilon. Alright, now let's define what strain is within the context of elasticity. Now, strain is simply equal to the ratio of the elongation or extension to the original length of a material. So we are saying that mathematically, we are saying that strain is equal to the ratio of the extension to the original length. The ratio, so we said that stress, which is epsilon, is the ratio of extension to original length. Extension or elongation as a symbol, it is being represented by E over original length, which is L. We can refer to this extension also as a deformation. as a deformation. You can see it as a deformation in some questions. It can appear as a deformation in some questions. So it might appear as elongation, it might appear as extension, and it might appear as elongation. Sorry, as deformation rather, as deformation. Alright, so that is that for strain. Alright, we measure the extension, remember, is a kind of length also, but it's an extended length. So measure this extension as what? As meters over, and length is also measured in what? In meters. In meters. So what happened here? Meters cancel out meters. So we have here 1. So we can say that strain has no SI unit. We can say that it is a dimensionless quantity. I've expressed how to, so I've done videos on how to, so I've done a particular video on dimensioning of physical quantities where we have some term being used as dimensionless quantity, dimensional homogeneity, and things like that. So for strain, we have this. Alright, now let's consider Young's modulus. Alright, now let's consider Young's modulus. And now Young's modulus can also be referred to as modulus of elasticity. Can also be referred to as modulus of elasticity. Now let's look into what the definition is. Young's modulus is simply the ratio of the stress on the material to the strain caused by it. Once again, Young's modulus is simply the ratio of the stress on the material to the strain caused by it. Alright, so mathematically, we are saying that stress having a symbol of our normal E, our normal alphabetical E, to be expressed as the ratio of stress to strain. The ratio of stress to strain. Now, we know the SI unit of stress to be Newton per meter squared over, we know that strain has no SI unit, so we have this. So it means the SI units for Young's modulus is Newton per meter squared. Now we said stress. How do you define stress? Remember, if we check the definition for stress, we said stress is the ratio of force to area. We said stress is the ratio of force on an elastic material to the area in which the force is applied. So we are saying that stress is ratio of force to area when it comes to an elastic material. So we express force to be over area. So we have this as stress. You have this. Everything over. Remember, we express strain as a ratio of extension to the original length. So we have extension over the original length. So we have this. You can express this one as, when I say this one as our Young's modulus E to be equal to force over area divided by extension over the original length. So we have this. And as usual, to change this sign from division to multiplication, we need to take the inverse of this side. So this one will come up This L will come up, this E will come down. So we're going to have our Young's modulus to be equal to F multiplied F over area multiplied by original length over extension. From there, we're going to have this, that Young's modulus now equal to F force times length over area multiplied by extension. So we have this as the expression for Young's modulus. The next thing now is to go into the calculations. All right. Example 1 now. Example 1 says that given that a load of 15 kilogram extends an elastic material of length 12 meter by 12 centimeter, full stop. If the cross section of the elastic material is 0.35 meters squared, find from figure 1 the force constant, from figure 2 find the stress, from figure 3 find the strain, from figure 4 find the Young's modulus. So we have that. All right. Question 1 says that calculate the force constant. Question 2 says calculate the stress. And question 3 says calculate strain. Question 4 says calculate Young's modulus. So we have this right here. All right, solution now. Solution for number 1. All right, let's recall force constant, which is K, equal to F over E. Before this, we should have listed our given parameters. All right, given, before them we should have this. Given, from the question we are given that a load of 15 kilogram. We are given a load of 15 kilogram. Also, we are also given the original length. Remember, the question says extends an elastic material of length 12 meter by 12 centimeter. So it's having a length of 12 meter and it's now been extended by another length of 12 centimeter. So the original length is what? Of the material is what? 12 meter. So we are having the original length of the material to be 12 meter. We're also given the extension. Extension is 12 centimeter. So we're having 12 centimeter. Remember, we need to convert this to meters, and that will be divided by 100. So 12 over 100, we're going to get 0.12. So we're having 2 0 here, so the point is going here twice. 1, 2 becomes 0.12. So we have 0.12 meters. So we have this. What again are we given? Okay, we are given the area to be what? 0.35 meters square. If we see meters square, it is telling you that it is area because the units for area is meter square. So you are having area area to be equal to 0.35 meter square. So we have this here. So we have this. All right, now let's move into the calculations. Calculations. Question one says calculate the force constant. All right, let's recall the formula for force constant, which equals to K equals to F over E. The formula for force constant equals to F over E. All right, our K equal to, now our force is what? Remember, if you look at the question very well, we are not given force, but we can find force. And the formula for force is given as F equal to mass times G, which is acceleration due to gravity. So if we have this, we can have our force to be equal to, our mass here is what? 15 kilogram multiplied by our G is a constant of 9.8 or 10. In most, if you are given as 10, use 10. But in this case, let's use 9.8. So our force, we multiply this 15 times 9.8, we're going to get 147. So that will be Newton. So this is our formula, our value for force here. So force is now given to be what there? 147 Newton. 147 Newton. So we have this. All right, we can proceed with our calculation now, since we have gotten force. All right, our force is given to be 147 Newton. 147 Newton. 147 Newton. Extension is given as 0.12 meter. 0.12 meter. So our force constant, we divide this. If we divide this, we are going to get, that will be 1,225 Newton per meter. So we have this as our final answer. Right, this is our final answer. Question 2 says that calculate the stress. Stress is given as sigma. Let's not forget, given as sigma. So how do we express stress? Let's not forget, stress is expressed as force over area, the ratio of force to area. So force here is given as what? Sigma. Force is given as what? 147 Newton. 147 Newton over area is given as 0.35 meter square. 0.35 meter square. So we have 0.35 meter square. So sigma becomes 147 divided by 0.35, give us what there? 420. Remember, here is Newton over, here is meter square. So we have Newton per meter square. So we have this. So question 3 says that we should calculate strain. Now strain having a symbol of epsilon equal to, remember, is a ratio of extension or elongation to original length. So we have E over original length. Remember, you can see it is on question as deformation. All right. So epsilon now equal to extension is given as 0.12 meter. So we have 0.12 meter over the original length is given as 12 meters. So we have 12 meters. Alright, if we divide further, strain which is epsilon. If we divide further, strain which is epsilon equal to 0.12 divided by 12 give us 0.01. Remember that strain has no SI units. So we have this as our final answer. Alright, lastly, we have to calculate Young's modulus. Young's modulus. So question 4, we have to calculate Young's modulus, which is a symbol, which is having a symbol of E. And remember, Young's modulus is having the formula of stress over strain. We have sigma over epsilon. Over epsilon, we have this. So Young's modulus equal to sigma, which is stress, is given as what there? 420 Newton per meter squared. So we have 420 over strain is given as 0.01. We have divided by 0.01. So Young's modulus, if we divide this, we are going to get 42,000 Newton per meter square. Remember that Young's modulus is sharing the same SI unit with stress. So this gives us our final answer. So I've done a video already on work done on a spring. That will be the part 3 video under elastic properties of a solid. So you can check that out and drop a comment as well. How you feel about the lesson, how maybe you get the explanation, or just drop a comment in the comment section. And do well to hit the like button to support this YouTube channel so that we can reach out to other students who are in need of knowledge as well. So this is Olagood Academy. Do well to hit the like button, subscribe, share, and follow for more. Thanks for watching.